So, okay. So today we will discuss about the P-space complexity class, um, P-space completeness, and Oracle Turing machines. The Okay, yeah, these are the major topics that we will look into. The Baker-Gill-Holloway theorem, that's something I'll record and upload. So, okay. Okay, so let's start with this question. So, P-space that we defined last time is simply the class of all languages that have a deterministic Turing machine that runs poly-sized space. Okay, so we know that P space is equal to NP space. The NP space is the non-deterministic analog, uh, where instead of the deterministic Turing machine you allow the non-deterministic Turing machine. But by Savage's theorem we know that uh, P space is same as NP space, and we do know that P is contained in P space because if a machine uses polynomial space, then uh, okay, sorry, yeah, if it runs in polynomial time, then it can only touch polynomial many spaces. So this containment is known. So yeah, so we have this P space class, and we know that log space is contained inside it. Okay. Okay, so like earlier, we need to define a notion of the some hardest languages for PSpace, which we will call PSpace complete. And and now the question is, how do we define the hardness? So what kind of reductions would be suitable for this? So we define, in this case we chose to define it as polynomial time reductions. So okay, so um, yeah. So the question is, okay, one language. Do we know languages here that are P-space complete? Do you recall it?
So quantified total true quantified Boolean formula was to the P-space.
Yes, correct. So we have TQBA for truly quantified Boolean formula, which is basically that you have a formula phi, and let's say it's on x1 to xn variables, then each variable has to be quantified. So you have something like, and so on. So yeah, so the question is whether there exists a variable x1 such that for all choices of x2 and so on. So we've quantified each variable, and based on that we are asking whether the formula is now satisfiable. Okay, so the question is, if uh, I mean, if I mean A is a piece-based hard language, then you want to show that it's also NP hard. So how do we show that?
So if a if a language is P-space hard, then it would mean that the language belongs to. So all the languages which are there in P-space can be reduced into this problem. And so since this language is going to take, say, a polynomial amount of the space, so then all those problems which are there in the P space are at least as hard as a NP problem is. So if a language is P space hard and all those problems are getting reduced into this problem, so clearly, I mean, this reduction will imply that all those problems which are there in NP can also be reduced into this problem. I mean, are not harder than this problem. So uh, Yes, because this P space is a superset of NP, and uh, right now I can think of this thing.
Okay, okay. So, okay. So that is intuitively, I mean, intuitively you would expect this P space to be much above NP. So, or I mean, to be proper subset of NP. So you would expect a hard language for P space to be hard for NP. But okay, so I mean, if we want to prove it, one way to do that would be that we show the deductions. So if I ask you to show that something is NP hard, generally what you do is you give me a reduction to, let's say, sorry um, some NP complete problem, so, or some NP hard problem. So if let's say L is LB P space hard language, if I want to show that it is NP hard, it's sufficient to show that L reduces to SAT. Right, that would imply that L is NP hard.
Yes.
Okay, so now, because the question says that this could be L is any P space hard language, actually you can just take a P space complete language. So for example, if you take TQBF, which is a P space complete language, then any hard language L reduces to TQBF.
Or, or rather, this should be in the reverse direction that since L is P space hard, so TQBF can be reduced into this problem L, and then we can remove all those existential or the universal quantifiers, and then this TQBF will become set, and then we can show that.
Hmm. So I mean, but this direction is what we are using, because this is the part 1 and this is the part 2.
But this should be in the reverse direction. I mean
Oh,
to say
sorry,
that
sorry, sorry,
TQBF.
sorry. Yeah, yeah, sorry. No. Sorry. Okay, so SAT reduces to L, and you have.
So by this L is getting
Hmm.
reduced to TQBF
Okay.
because the TQBF should get
Yes.
reduced into L.
Yeah. Okay. So, so this part follows from the definition uh, of P space complete language, because L is a P space complete language. So in particular, TQPF will also reduce to it.
Right.
Okay, and this is what we need to show. So, yeah. So how do we do this?
But then set, I mean, TQBF is at least as hard as the set problem is because TQBF comprises of the quantifiers as well. And whereas in the set, we do not have any quantifier.
Hmm.
Or at the most in the set, we use a dummy alternative universal and the existential quantifier so that it becomes an instance of the TQBF. And that would be something which is true. I mean, if we have a satisfiable instance and irrespective of the values assigned to those dummy variables.
Okay. So, yeah, in fact, when we say that phi is satisfiable, what we are actually saying is that there exists an x1, there exists x2, and so on, there exists xn. So, there is some assignment to variables that will make the formula satisfiable. So, this is exactly what we're saying.
Yes, yes. Now,
Huh.
now we can introduce the universal quantifiers and which would be comprised of the dummy variables. Like, and
Uh,
alternatively, we can introduce.
yeah, so actually, the TQ does not insist that you should always have universal quantifier. So it is okay that some variables that all are there exist quantifiers. The
Okay,
only thing it wants is every variable should be quantified. It should not be that some variable is hanging around and not in the scope of quantify.
okay, okay.
Okay, so this is a perfectly valid TQBF instance. So yeah, so that's the only reduction. So basically we're just taking the formula and writing this um, existential quantification, and yeah, and solve the TQBF instance, and you get back the solution to SAT. Okay, so okay, that completes the proof. Yeah, I'll do one simple exercise on um, closure properties of P space.
So if L1 is P space and if L2 is P space, then clearly the union of L1 and L2 can also be would also be decidable by. But then since okay, so then what we can do that so if we have if L1 is P space, then we have a machine M1 and which runs in the poly space, and if L2 is P space, we have a machine M2, and then for this union thing, we would be running these machines in parallel, so that that may give the proof that either the first machine will
Hmm.
decide or the second machine will decide. So union is tough. And for the complementation thing, what I need, I just need to probably the if L1 is P space, then its complement would also be P space. Would mean I just need to reverse the signals or what, or and then this star thing, if L1 is P space, then the cleaning closure of L1 uh, would also be P space. And how can we ensure this? Yes, that we can do. That we can do because if L1 is is there in P space, then L1 square would also be in the P space in the sense, and then similarly L cube because I don't know, because we can reuse the space kind of thing or what.
Hmm. That is that is going to be the main idea. Okay, let me first write down the other two. So the idea for union is correct. So you know that L1 L2 are in P space. So there is some deterministic Turing machine M1 for this, and some deterministic Turing machine M2 for this. Both of them run in P space. So the idea is that you can you can do parallelly in this case, because um, I mean, uh, if first one uses P of n and second one uses Q of n, that is still a polynomial, adding up those spaces. So that is fine in this case. So yeah, so either run both parallelly, or you can even do um, separately. So run m1 m2, and if both accept, so if either accepts, then accept, otherwise reject. So that's the idea. And in the complementation, it's um, simply that you run m1 and flip the answers. If m1 accepts, then reject, and if m1 rejects, then accept. And the idea for uh, intersection is also is also very similar. In fact, since it's closed under union as well as complementation, it follows that it's closed under intersection. So what we need to show is the start. So okay, so what does L1 star look like? So it's going to be the um, mm, I'll call it x1 x2 to xk, such that each xi is in L L1. Okay, so the point is, if I give you this input as 0 1 0 1 and so on, so this entire thing, this concatenation of x1 to xk, is actually one single string, where I don't know which part, where does x1 end. So maybe x1 is this part, and x2 is the string up to here, and so on. So there is some kind of a partition that is there, but I don't know which is the correct partition. So if I interpret it like this is x1 x2 and so on up to xk, then I can run my machine on each of them and check if all of them are in L1, and if all are x1, x2, and so on up to xk, if all are in the language L1, then we will accept. But the only confusion is how do we find out what is the correct partition?
Yes, but then this is cleaning closure of L1, so wouldn't it mean that L1 union and then the I mean L1 can be repeated any number of the times, including null. Uh, so if L1 can be repeated any number of the times, including null,
Hmm.
so I mean through this division, I mean what are we trying to achieve? That if this concatenation, this entire concatenation is the element of L1, then what do we want to show? That each, I mean, we have to divide this concatenated string in such a way so that every division also belongs to the language L1, or what?
Ah, so okay, so let's look at your example. Okay, so we have L1, sorry, L1 star is L1 union, and so on. Okay, so um, okay, so now if you want to check whether x is in L1 star, what you will do is you will actually use the closure property of of under union, right? So in order for x to be in L1 star, you're saying it should either be in one of these, L1 cube, L1 square, and so on.
Yes.
Okay, so now all that remains to do is to show that each of these, say L1 to the k for k greater than equal to 0, is actually uh, can be done in p space.
Uh, yes. So can be done in the P space. Why so? Because I mean, why so? Any specific reason for this? Because the polynomial raised to the power polynomial is still a polynomial, or what?
Hmm. So that's what we are trying to do here. So what does an input of L1 to the k look like? It is some. Hmm. So okay. So that basically means there is some uh, input of length k. Then there's some other input. I mean, sorry. Hmm. There is some input x1 that is there in L1, then there's some other input x2 that is there in L1, and so on. So there are k many inputs that we know are in L1, and if you take a concatenation of them, then that the resultant string is also in L1 to the k.
Yes.
That is what it means. Okay, but if what does this input actually look like? It's basically 0 1 strings, zero.
Correct.
Okay, so and the strings that are there in L1 could be something like 0 0 1 1 0 1 1 1 1 0 0 0, and so on. So it all the input lengths of the strings that are there in the language could be very different.
Yes.
Okay, so okay, for example, if I include this 0 1 0 in this, then this could be my x1, and and so on. So I'll have to find out what is the correct partition. It could also be that if I divide it like this, if I choose 0 1 0 to be my x1, then I'm forced to start x2 from here, and maybe I will not get a valid x2 because I chose it wrongly. But maybe 0 1 0 0 1 was also here. So if I choose this to be my x1, then I get a valid x2, 0 1 0.
Yes.
Okay, so So I can't, if as a binary string, I don't know what is the correct partition that it should be. For some partition, if it accepts, that means we should accept.
Right.
So we just want to find out whether there is a partition which will make all the k strings uh, be in the language. So that is, yeah, so that is the part, that detail that we need to take care of. So what would be um, like obvious, maybe like brute force type approach of doing this?
Yes. So then the brute force thing would be like, say, I keep on incrementing this divider
Hmm.
by one amount and keep on asking to my Turing machine,
Hmm.
will you accept this string?
Hmm.
And I keep on incrementing the divider. So at one point, and I would be making polynomial number of the moves of the divider,
Hmm.
and then I will get my first string, and which would be decidable by the which is decidable by the Turing machine.
Hmm.
And so then I will eliminate the tape, remove the content of the tape, and then I shall start looking for the second string.
Hmm.
And since even though the string could be pretty large, but then this string would be of the finite length, or I mean, would be in the polynomial. Its size will be polynomial.
Hmm.
So effectively, I would be erasing the content of the tape of the Turing machine, say polynomial number of the times. So even though this may take lots of time,
Hmm.
or maybe exponential time, but then I would be able to decide this entire thing in the polynomial space because that tape can be reused.
Hmm. Okay. So the idea is correct. Only thing is that the number of um, so we will go through all possible partitions of x1 to xk. So that count could actually be very large. It could be exponential because I mean, let's first do a very naive way of counting. So I want one counter to tell me where x1 starts. Um, so I'll call it p1. The other pointer to tell me where x2 starts. Third pointer to tell me where x3 starts, and so on. So I'll need, okay, p1 is redundant because of course um, it starts from the first bit. So I'll call p1 to be the end of first string, p2 to be the uh, end of the second string, and pk minus 1. These many counters are what we need. So p1 can be anywhere between 1 and n, where n is the length of the input. So p2 can be anywhere between p1 and p1 plus 1 and n, and so on. Okay, so this is pk minus 1 plus 1 up to n. So if we do a very I mean, for now, as a first attempt, if we do a very loose counting, p1 is at most n, each pi is at most n. So for every I mean, there are n many choices for each of these pi's. So altogether you have n to the k minus 1 many possible um,
Yes,
partitions.
but then this quantity is still polynomial.
Okay, if you choose k to be a constant, this is still polynomial. So you could okay, yeah, this will work. Okay, good. Okay, what I was thinking earlier was that if you don't look at it as this union, then what you will have to do is you don't even know what the k is. So then you need a better way of doing it. But this is more cleaner if we do it this way. Okay. Okay, good. So because you have only polynomially many partitions to go across, we will reuse that space again and again, and check for each partition whether that works. Okay, good. So I'll just quickly write the steps. So for each partition x1 to xk, okay. So yeah, okay, so this will work in PSPACE. Okay, so now we can ask the same questions, the closure properties, but instead of PSPACE, let's ask if the same thing works for NL, because now we don't have this polynomially large space to exploit like we did in at some places, but let's see whether that works out if we have log space with non-deterministic machine. So union and intersection might be very similar.
Yes, because if language is NL, then I have NTM and deciding everything in the logarithmic space. So for the union, it's okay. So if L1 is decidable in logarithmic space, L2 is logarithmic. So we can use a similar approach for the union. We will run both the Turing machines in parallel. And for the complement thing, won't be difficult. Again, we can flip the things and it will become complement. And then union and complement, we apply De Morgan for the intersection thing. And now the only thing left is for the star. And then for the star, since now I can use only logarithmic amount of the space, so how to manage those counters then? But then I can. But this time, this time I have non-determinism available to me.
Hmm.
So how can I use the non-determinism and along with the count stuff to decide the cleaning closure of L? So non-determinism probably will tell me that okay, this K ends here, and you stop here, and this is the first string, mysteriously, magically, and then I just need to keep the counter thing only one variable, and that can be done. I mean, with this NL, I guess.
Yeah, good. So yeah, that is exactly the idea. So union and intersection will work similar as earlier, but yeah, but for the star, we need to go through the partitions, and the luxury that PSPACE gave us was that because we have polynomial space available to us, we could go through all of them, which which is something we can't do with log space because we don't simply have that much space. So like you said, we'll use the non-determinism that is given to us. So what we will do is we will guess the partition x1 to xk, and now that we have the partition, it's same as what we did for union. Check for each of them, and if all of them accept, then we're going to accept. So run the machine for union. Okay, not really union, it's intersection. Okay, so yeah, so that was the key point. Good. mm,
I have a question at this point. So, will this be true for the give just L as well? I guess no.
no.
No. Yes. Okay. Okay. And for L, what would be true? The union thing would be true. The
Uh,
complement thing would be true. Intersection would be true, but then star won't be true. Is
Star
this?
we don't know. don't know whether it is true.
Oh, we don't know.
Hmm.
Oh, I guess. Okay, all right.
Okay, so I think this is a final question on the p space part. So you have TQBF instance, which is there exist. Okay, let's say, I mean, some quantification that we have. Um, okay, and this V earlier was allowed to be any formula, but now let's say the formula is very special and we are only allowing it to be in the conjunctive normal form. So um, what we want to show is that this new TQBF instance, which I'll call TQBF tilde, we want to show that this is p-space complete.
Yes. So, but I don't exactly remember that proof that TQBF is p-space complete, but clearly, I mean, even if we write the Boolean formula in the CNF, this is element of the p-space, no doubt in this. And then because we need to show that this TQBF can be reduced into this TQBF tilde in the polynomial time.
Hmm.
So any Boolean formula, I guess any Boolean formula can be written into the CNF.
Hmm.
There is no issue
Hmm.
with that.
Hmm.
That can be done in the polynomial
Polynomials.
time.
Yeah.
So yeah, is this a proof? Yeah,
Yeah, yeah.
I guess.
So we can, yeah, we'll use the fact that TQBF is p-space complete, and it's sufficient to reduce it to this new problem that we're defining, and for that it's sufficient to show that um, any formula phi can be converted to a CNF instance psi, which can be done in polynomial time. So yeah, the idea is, I mean, simply that I'm okay, and we've done this already in the SAT world. I think we showed that circuit SAT reduces to CNF SAT, and CNF SAT further reduces to 3 CNF SAT. So it's the same idea.
Yes, but
Um,
then I have a question here. On that day, you said that this DNF is something else. I mean, that is CNF is NP-complete. However, this disjunctive normal form is pretty easy.
hmm.
But then I forgot. I mean, why did you say this thing?
um, so what we did that day was we looked at the depth restrictions, no? Um, so we did something like okay.
So if I take uh, so
Hmm.
because the CNF would be
Hmm.
uh, the conjunctive normal form would mean that this is the CNF would be the end would be the or of the ends,
Hmm.
I guess,
Yeah, so this is
or of the ends, and this DNF would be the end of the ors.
hmm.
Uh,
Yeah. So what was happening there was, for this to be true, we wanted all these OR gates to be true.
yes,
But for OR to be true, you only need one of them to be one of the inputs to be true. So
yes.
that somehow gives us a lot of freedom. Whereas if it were a CNF, um, then okay, what else? Oh, sorry. I think I wrote the other way around, no? Mm,
Yes, because DNF
hmm.
is DNF is OR.
Right.
So then This
Yeah,
could be
sorry.
the
This
or
is
of the
CMF.
and.
Right. Yeah. Okay. Okay, so we'll go through it again. So this is easy because for this to be true, you only want one of these to be true. Um,
Yes.
okay, so this was easy to find out, but here for this to be true, you want all of them to be true. So there are some constraints that will add up. Okay.
Yes. Yes. Right. And if we take the complement
Hmm.
thing, then
Hmm.
probably the co-NP etc. will come into the picture and not NP.
Hmm.
So this DNF might be having some relation. DNF is not NP complete. Is this correct?
Yeah.
Okay. So if DNF is not NP complete, then probably DNF might be having some relation. But then if a language is NP complete, then then its complement is co-NP complete.
Hmm.
Uh,
Hmm. So, but
yes.
hmm. But then what we're doing is if when we're asking if P is satisfiable, um, okay. So when we take a negation of this, okay. I mean this is um,
I
it
understood.
becomes
Yes.
a
If we
yeah
take
it
its
becomes
negation,
a
then it will become unsatisfiable kind of thing. Yeah. And the
huh,
problem would be
or
altogether different. Right.
unsatisfiable, or it's same as asking whether it is tautology.
Yes.
Hmm. So which we know is yeah. So although this becomes a DNF format, we are asking a different question.
Right. Thanks.
Okay. Yeah. Okay. So now we'll talk about this idea of Oracle Turing machines. Okay. So the idea is that we have this class NP, we have this class P, and we have some hard problems here, and uh, yeah, and like we understand there are several problems here that we don't know where will they go. Okay, so what Ladner shows is that if assuming that this class NP is different from P, it cannot be that the picture looks like this. So it cannot be that this is NP, you have NP complete problems and then the rest are P problems. It cannot be that it looks like this. So if P is not equal to NP, then there exist languages in NP such that they are neither in P nor in NP complete. So it will look something like this. If P is not equal to NP, there will be languages here. So um, yeah, so the point is that what this sort of tells us is that if there is some kind of a hierarchy even within the languages in NP, so there are some very hard problems, there are some some problems that are not as hard as them. So how do we measure which one is harder and how hard it is? So the Oracle Turing machine sort of gives us one way of defining a measure, which says that okay, let's say uh, some problem. I mean, it's not just within NP, but in general, we are defining how hard is one language compared to the other. So let's say I say that A and B are maybe, let's say, in okay, I don't know which class would be a good, okay, but let's say A and B are both hard problems, and let's say A with access to a SAT oracle. What do we mean by access to SAT oracle? It means you can ask it any queries of the that are inputs to satisfiability, and assume that the answers will be given to you for free. So you don't have to solve the SAT explicitly, just ask the oracle and it will magically solve it and tell you whether the formula is satisfiable or not. So that's the idea behind the Oracle Turing machines. Or in terms of machines, you can think of it as having an input tape, having a work tape, and also having an Oracle tape where you will get answers to your queries, Oracle queries. So it will tell you 0 if it's false, 1 if it's true, and so on. So, okay. So, so the question is, if I give you uh, access to SAT, or Oracle access to SAT, and if B is also given an Oracle access to SAT problem, then are these problems equally hard now? Or maybe now this problem falls into P, and this is, let's say, still in NP or something. So, or maybe something else, I don't know, Sigma 2 or something. So, it could be that, let's say, these two problems were NP hard earlier, but B is much, much harder. Sorry, A is much, much harder than B, so much that even an Oracle access to SAT makes it hard, but B becomes easy. So this somehow tells us that how to compare the hardness of two languages, and SAT is just one Oracle. There could be, you can think of some other Oracle and see um, how the hardness changes after that. So that's the idea behind defining the Oracle Turing machines. So
So I have a question here. That so I could not understand the relation in between this. I forgot the name of the theorem. Can you show the name of the theorem? This.
Ladner's, yeah.
Yes, Ladner's theorem. Yeah. So I mean, what's the relation in between the Ladner's theorem and this Oracle Turing machine? Ladner's theorem probably only say that if NP is not P is not equals to NP,
Hmm.
then there would be a hierarchy among the NP class problems as well,
Hmm.
and then there would be NP class problems which are not NP complete. And last time you discussed the graph isomorphism and this whether is primes. So all these problems are there in this region,
Hmm.
and you call them NP intermediate
Hmm.
problems.
Hmm.
So now, but then with this Oracle thing, so I mean, what's the
Okay, so what
relation
I'm
in
huh.
between?
So the Oracle thing is something that just gives us a philosophy, but we are not just applying it to the NP class. So the idea just here is just that there could be a hierarchy of hardness within NP. This is what this says, right? So even if P is not equal to NP, it's not that there are some problems that are very hard and some problems that are easy. Rather, there is some kind of a hierarchy that these are easy problems, these are very hard problems, and then there are problems in between.
Oh, I see. So say if instead of the set, if we would have been given something like say and how to pronounce it, raised to the power NP or what? A raised to the power NP or A
Um,
NP and then P NP. Then will this change?
which one? This one?
Because
Okay.
so instead of set, I mean set
Okay.
can be replaced. Set can be replaced by a complete complexity class also. So like say I can write A raised to the power NP
Hmm.
and then p raised to the power np. Then if a is much harder compared to the b, then what about the languages a raised to the power np and then b raised to the power np?
Okay. So, okay, one thing is, okay, generally, I mean, just a matter of, I mean, calling it. So, I generally call it A with Oracle access to SAT. But, okay, so the point is that I mean, this Oracle access that we are giving is always a language. It cannot be a class. So, uh, because what is the input that goes to it? Input is, uh, I mean, there will be, let's say, a formula phi in this case that I want to solve, but I will not solve it. I just have a solution to one problem, which is in this case SAT. So I will ask some Oracle to solve that problem for me, and it will only tell me whether it is satisfiable or not.
So I
So,
might have forgotten the things, but probably in the lecture it was given somewhere that this need not to be
so
a language and it could be a complexity class as well. Like we can say something like say uh, p raised to the power np kind of a thing.
so
Oracle access to np or something similar.
okay, so what? Okay, so I think I need to check it, but I think if it's written that way, then it probably means that it's some NP complete problem. Some you can choose any canonical NP complete problem. So instead of, you can even take SAT or vertex cover or something. But as far as I recall, you have defined this model with respect to a problem. Um, but okay, I'll get back to it. But okay, I'll check that.
Oh, okay, all
Okay,
right, fine.
okay. So, so what was your question, or though, that if instead of
So my query is that now it will depend on, so the relative hardness of, quite possible that A could be harder than the problem B. However, within Oracle access, quite possible that A becomes easier
hmm,
than the problem B. So this may happen. Is
this may
this?
happen, yeah. So
Uh,
Oracle, yeah. So it may not always give you a very yeah, very logical, I mean, sort of conductance that we expect. In fact, that is something you'll see some um, hints of that in the Baker-Gill-Solvay theorem, which we'll do next time. So it's not a very clean uh, characterization, because again the question is, we don't know what is the right way of measuring the hardness. So this is maybe just something intuitive that that comes up, but it may not give us a very nice classification.
so what this Oracle, I mean, access to the Oracle does? So it establishes the membership or
Exactly,
something
exactly.
else
Yes, yes.
first.
It will only check the membership and yeah, tell the answer to that. Yeah.
Okay, okay.
Okay. So yeah, so let's do one question of that kind. So we'll define this unique SAT problem as a modification of the SAT problem, where instead of having some satisfying assignment, we have exactly one satisfying assignment. So yeah, so start.
So I think since phi is a Boolean formula and which has got, so all the Boolean formulas which have got just one satisfying assignment would become the part of it. So now the thing is that this can be decided by a simple DTM, but then this DTM, deterministic Turing machine, but then this deterministic Turing machine has an access to the set oracle, and the set oracle will tell in the constant amount of the time that do we have, I mean, is this the element of the satisfiability or not? But it will not tell us that whether it has exactly one satisfying assignment or not.
Hmm.
So for that thing, what I can do, if a Boolean formula has only one satisfying assignment and not many, so how to ensure the uniqueness of the Boolean formula? Probably I can take the union of this Boolean formula with what? With if I take the union of this Boolean formula with itself, so what will happen? No, no, no. If I take the intersection, no, this won't work. So how to ensure that this oracle gives say yes only when this Boolean formula has a single satisfying assignment?
Yeah. So okay, I'll just write down what you said just now. So that is correct. So what you'll do is, first we will ask the Oracle Turing machine whether phi has a satisfying assignment, and if it says yes, or if it says no, then if it doesn't have any satisfying assignment, we will already reject. Okay. Now in the other case, we know that there exists at least one satisfying assignment. Okay, now we want to differentiate between the cases when this is exactly 1 or greater than 1. So the idea that you're saying is actually along the very, I mean, along correct line. So I have this formula phi, and we want to do some modification, some kind of surgery to it, to obtain a psi prime Okay. Mm, okay, 1 second. Hmm. Such that psi prime does not have. So if let's say I somehow know this, I'm assuming at the moment that I know this. There is an satisfying assignment. I'll call it A, and I know A. That is what I'm assuming. So we have access to A, which is a satisfying assignment for phi. Okay. So now what I'll do is I'll construct a psi which does not have A as its satisfying assignment, but everything else is same. So every other satisfying assignment B, if B satisfies phi, if and only if B satisfies psi. Okay. So basically psi is same as phi, only that this particular assignment A is not does not satisfy phi. So if we could somehow get such a psi, then uh, then what will you, like, let's say you have access to psi, then what do we do after this?
So if I somehow if I can construct say psi from the phi,
Hmm.
then I will ask for phi. I will ask to the OTM
Exactly.
that okay, does this have a satisfying assignment? And the OTM must say uh, because this is getting satisfied for so many B's,
Hmm.
but then it is not satisfying for A only.
Hmm.
So then I will ask the OTM that okay, so then this OTM probably won't be required. But then how to know that whether this has a satisfying assignment or not? So okay, this has become so complicated.
Okay,
So
so let's go
because yeah.
step by step. Okay, so we will ask OTM if psi is satisfiable. So ask OTM if psi is satisfiable. Okay, so if psi says yes, sorry, OTM says yes, then what does that mean?
That would mean that it has got a satisfiable assignment, but then this satisfiable assignment could be, but then this phi, in case if phi is having many satisfying assignments, say for example,
Hmm.
and I have just excluded only one assignment A from it,
Hmm.
from psi,
Hmm.
then this OTM will say yes, and but how to ensure that the yes of the OTM does not include an small a. Yes, definitely, because we have instrument this psi in such a way
Hmm.
so that for A it is not satisfiable, and for I mean for all other satisfying assignments would remain the same.
Hmm.
So if OTM says yes, so that assignment should be a B only and cannot be an A.
Hmm. So that means phi also has some other assignment.
Yes.
So therefore there exists B that satisfies phi. That means phi has more than one satisfying assignment, because A already satisfied phi. Now we know there is something other than A also that satisfies phi.
Yes. So this phi is not the part of our user language.
Hmm. Okay.
However, if the answer is no,
No.
then because we know that so if answer is no, so no would mean two things, that either the phi has no satisfying assignment or the phi has only one satisfying assignment, and that is small a.
Yeah. Then it has. Then phi has only a single satisfying assignment.
But it could be the case that phi has no satisfying assignment as well.
That we already checked in the first query. So
Oh
let
yes, 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 right.
then phi has a single satisfying assignment. So actually we can even think of defining complexity of two problems with the same oracle, but you can like fine grain it further by saying how many queries did you need. So in this case, let's say we asked two queries. This was once where we asked for fee. This was the second satisfiability query for psi that we asked. So this is actually called uh, p to the sat of 2. The 2 here tells you that you asked two satisfiability queries. In general, if you ask k many queries, then you can call it p to the sat of k. So again, this gives us a more fine-grained notion of comparing two classes, how many, based on how many queries it needed and so on. So I mean, it can go on further, like you can define more things, but okay, that's it's a side thing. The more important thing is that there are two things that we did not uh, that we assumed here, that we will have to concretely solve. So one is that we assumed that we know what the satisfying assignment is, because this oracle will only tell you whether it has a satisfying assignment or not. It will not tell us what that assignment was. So this is something that we assumed for constructing psi, and we also need to show how to construct psi. Even if I know an a, using a and phi, how do we get to psi? So these are the two things that were in the black box. So okay, so okay, so let's do the first part. How do we, okay, phi is, we know that phi is a satisfiable formula, and now we want an assignment, or I'll call it explicit assignment, a for phi. So this is the first part that we want. So any idea how do we proceed?
So, so we want this explicit assignment A45, but how to get this assignment? Yeah.
Yeah, so here we'll use one very nice property of satisfiability problem, which is called self-reducibility. In fact, most NP complete languages, or at least all the NP complete languages that we know, do satisfy this property of self-reducibility. So what does that mean? The idea is that if I want to solve a big problem, it can use its own solutions to smaller problems to construct the solution to the bigger problem. So for example, phi here is a formula on n variables. So what I'll do is, I'll ask what is the assignment for x1. It can either be 0 or it can be 1. So let's say x1 is equal to 0 or x1 is equal to 1. Now this reduces to another formula, phi prime, or I'll call it phi1 for now, where x1 is uh, vanished. I mean, it's replaced with 0, so you can simplify it, and x1 is out of the picture now, and you have another formula which is on n minus 1 variables. Similarly, in this case, we will get another formula that is on n minus 1 variables. Now the question is, if I know the answer to this, if either one of these is yes, if either, or let's say, let's do it this way. So let's say this is yes, if I have some solution, someone solving this instance for me, this satisfiability instance, if this is satisfiable, then I know that phi is satisfiable, right?
But then who will tell me that after making the value of x1 as 0, this entire formula is satisfied?
Exactly. So then what you do is you do the same process. So think of starting at this point and asking whether x2 is, if I put x2 as 0 or x2 as 1, then, or let me extrapolate it here. So let's say I ask, okay, I know that okay phi 2 is satisfiable. So what I'll do is I'll ask, okay, if I put x2 is 0 or x2 as 1, what about this new formula? Okay, so what about this new formula, whether this is satisfiable or this is satisfiable?
But then who is going to tell me this? I mean the result, the OTM or
Okay, so when we define the self-reducibility property, we are not using OTM in picture. Okay, so we are just saying that the only thing that we are concluding from this is that if I want to solve for a bigger problem which is on n variables, I can use the solution to the smaller problems which is on n minus 1 variables to construct the original solution.
so that is that this is the very primitive idea we use in programming, like say recursion.
Yes, yes, yes. But
Recursion is
hmm,
self-reducibility only.
yes, but you will be surprised that this property is not that easily satisfied. For example, if you look at languages up in the hierarchy, um, many languages will not satisfy this property. So
Oh,
even let's say even the NP intermediate problems, some of these we don't know whether this is true. So for example, let's say the minimum circuit size problem, or the uh, yeah, there it's not intuitive why solving for a smaller circuit will give you solution for a bigger circuit, or it's not clear how. In this case it joins up very obviously that it's just an or of those two, but there it's not clear what to do. Even graph isomorphism may not be trivial, so even if you get solutions to smaller graphs, okay there.
so like
hmm, hmm,
so like say, I mean, what would be the smaller problem instance of a graph isomorphism problem?
hmm,
So if I remove some of the vertices,
hmm,
then I am destroying the structure of the problem instance
hmm.
as such.
Also the choice of vertex that you chose will also make a difference.
Yes. So because the self-reducibility as
hmm,
far as the recursion in the programming is concerned,
hmm,
so is applicable only when we find subproblem,
hmm,
and that should be exactly same as the original problem.
hmm,
So in the languages, whenever we find that the problem is like this, that we can reduce it into the subproblem,
hmm,
then probably this idea of the self-reducibility will come.
hmm. And yeah, and also like even if we have the solution to the sub problems, how do we join them together to get the original solution? That also may not be clear at several points. Yeah.
Yes.
Okay, so now with this, with because of this property, and because of the fact that now we have the access to Oracle Turing machine, so this 2 that I wrote here may not be 2 anymore because we are actually going to use it many times. So yeah.
I have a query at this point.
Huh.
So you wrote that the self-reducibility is a typical characteristic of NP
Hmm.
NP complete languages. And is this because this is true for the satisfiability, and we would be reducing the satisfiability to the other problems? So since it is true for the satisfiability, it is by default true for the other NP complete language as well,
Uh,
or there is some other reason?
there is some other proof for this, which is I don't think it was very involved, but it's not fresh in my mind. But yeah, I think if you Google this, you'll find some proper proof of this.
Okay, okay, sure.
So, hmm. Mm, yeah. So now we were at this point where we asked the OTM whether phi is satisfiable at all. If it says no, then we were anyway rejecting. But now we know that there is some satisfying assignment. So we are here. Okay. Now what we're going to do is, the next step is that we're going to construct this A. So we are at this point where we know that there is a satisfying assignment. So if there is a satisfying assignment, either it will put x1 as 0 or it will put x1 as 1. So we will branch out here and ask the Oracle Turing machine whether this is satisfiable. If it says yes, then we will go further. So we'll go further and ask, okay, if I put x2 as 0 or x2 as 1, then whether it is satisfiable. So at most I need to make two queries at every level. So at the first level, if in order to find out the correct value of x1, I needed to make, okay, I really don't even need two queries, because one query is enough, right? Because if this says yes, then I'll explore this branch. If it says no, then I anyway know that it's 1, so I will explore this branch. So at every level I'm asking one query. After n queries, I'll know the value of the setting of x1 to xn, which makes it true.
But then what would be the length of such a tree?
So at every level we are eliminating one variable. So here x1 is eliminated. In the next level x2 is eliminated. So after
Uh,
n
so
levels,
the height,
huh,
height would be n. But if the height is n, then we can solve the satisfiability problem in the polynomial time. Then I mean, why
uh,
this is there in NP and NP complete too?
if height is n, then there are these. Okay, I didn't exactly understand your question. So,
So since the height of the tree is n,
hmm,
so it means that we can find one satisfying assignment if it exists for any given Boolean formula
hmm,
in how many iterations. So at every level,
hmm,
I just need to make two decisions. Is
hmm,
this
hmm,
whether to go this or
hmm,
to go that?
hmm.
And so then 2 plus 2 plus 2.
This will
So
be.
at every level, we
Hmm.
would be making two decisions.
So these are exponential, right? Because
See,
hmm,
I make two decisions on the level 0,
hmm.
and I make one decision at this node.
So
No.
this is because we are assuming that we have access to this at. So here we are using the uh, OTM's answer. That's why we are eliminating these possibilities. Because
Oh, I see, I
huh,
see, I see.
otherwise if we don't have access to it, then this will be exponentially many possibilities.
Right, right.
Okay. So OTM is kind of guiding us through the assignment. It's just giving us the path. Hmm.
Yes, and we would be asking OTM multiple number of the
And
time.
many, huh.
All right.
So then we ended up using SAT uh, 2 plus k plus sorry n plus 2 many queries at this point. So also notice that you are only allowed to make polynomially many queries to it to the Oracle, because you have limited time, like you have polynomial amount of time with you, so the number of queries can never exceed the time that you have anyway. So this has to be polynomial. And so that gives us, like, from here we are here now, we know the satisfying assignment A, and now the only thing that is remaining is to show that if I have this phi and the satisfying assignment A, then how do we get this phi that satisfies this constraint. So we have a phi which is satisfiable, phi, and A which is a satisfying assignment for phi, and we want to convert this to psi such that for all b not equal to a, b satisfies phi if and only if b satisfies psi. So essentially what we want to do is that we want we want to append something to this psi such that this is not true. Okay, so what we will basically do is, so for example, if it says that x1 is 0, or let me just write it in terms of, so maybe the satisfying assignment was 0 1 1 1 0 whatever. Okay, so what I'll do is I'll just make this
So take the end of these values. So 0 and 1 and 0 and 1 1 1 and then 0,
hmm,
and then you include its complement with
hmm,
with 5,
hmm.
with psi, say.
Exactly. So
So then,
yeah, so we're saying that it is not that x1 is 0 and x2 is 1 and x3 is 0 and so on. So we are basically writing the 0 1 assignments in terms of variables, and we don't want this assignment to ever be true. So if we apply the De Morgans, this will give us x1 or x2 bar, or sorry, or x3 and so on, or xn. So yeah, so this ensures that if such an assignment 2x1 2xn is given, then this part of the formula will become false, and therefore the entire formula, sorry, I think this should be phi, right? Phi and yeah. So this just ensures that this particular assignment can never uh, yeah, I mean, if it appears, the formula will necessarily um, become false. And also, if we substitute anything other than a, so let's say b not equal to a, okay, then this formula is always going to be true.
yes, yes,
Okay,
right.
so then this I'll call this phi prime, then phi prime is always true. Therefore therefore psi is satisfiable, or psi of b is true if and only if phi of b is true. Okay, so that ensures this guarantee.
Yes,
Okay,
yes.
now if I modify the question slightly, if instead of I defining a unique set, if I define this to be, let's say instead of single, I want three satisfying assignments, then what are the changes that we need to do?
So if I want a finite number of the assignments, uh, so then yeah, so then I have to I mean uh, so then with so if there are finite number of the assignments, then can this mechanism give us the multiple number of the
Hmm.
assignments? The mechanism which we follow just now, probably it will give the multiple number of the assignments, because okay, so in that case I'll have to take this end with the those three number of the
Hmm.
Boolean formulas.
Yeah, so you will have to basically repeat this idea over and over again. So yeah, I mean, at this point, if you know that there is an assignment, we will find a psi which does not take that assignment. Now do the same process again. So at this point we will ask psi to construct one more assignment and mask it further to construct one more psi prime, so that instead of this a, we are actually getting 2 3 assignments. So a1 a2 a3, these are the three assignments that we will eventually have, and then we will do this process.
So I mean, can we have, so if when I ask something to the OTM, it gives me an answer. And say if multiple number of the answers are possible for a particular problem. So
What do
then
you?
is so if is this possible that so if a problem has multiple number of the solutions,
Huh.
and multiple number of the solutions would mean that okay, so multiple number of the solutions, and now if I take the help of the OTM, so OTM gives me, answers me, uh, that is this the solution of the problem? So OTM will say yes. Okay, so I'll have to ask OTM multiple number of the times to get, I mean, all the satisfying assignments. Is this the case?
Yeah, you will actually have to build the satisfying assignment, because notice that it only tells us that whether it is satisfiable or not. What we had to do was ask it several number of times to construct that assignment.
Oh, and do we have such an Oracle Turing machine, and which has got some uncertainty as well? And like say, it may give me the right response with two-third of the probability, and wrong response, say one-third of the probability. And moreover, does this make any sense to include uncertainty component and with the Oracle Turing machine, like which happens in the probabilistic complexity classes?
Okay. So, okay, so you mean like, I think, yeah, there are results of that kind where you have this RP, BPP, um, I mean, given as Oracle. And again, what I think I need to look into what we mean by giving the class. Do we give a complete language, or, uh, yeah, or, yeah, I need to understand what that means. But I think, yeah, there are languages that, I mean, that are defined like that. So if you give access to those probabilistic randomized classes, yeah, then what are the consequences and so on. Not sure if that will come up in the course, but
So yeah, so there are two questions. One is that we have got access to a, complexity class, and which is of probabilistic in nature. One thing, like say we give the access to RP or PPP kind of the thing. The second thing is that it becomes the nature of the OTM itself. That OTM has got some kind of the inbuilt uncertainty that okay, I will establish the membership of to the language, but then I would be true only two-third of the time, and one-third of the time, even being an oracle, I may not be true. Do we have
yeah.
something of the sort?
Hmm. Yeah, for ZPP for sure, because uh, I mean, because it will tell you the correct answer, or it will say that I don't know.
So
So
yes, so
it has some.
don't know facility. Yeah.
Hmm. It has this thing. So ZPP definitely makes sense, but RP and BPP where you have some kind of error. So. Mm,
So my query is slightly different from this RP and BPP thing.
oh, okay,
My,
okay,
my,
okay.
my, my,
Uh huh.
my query is that in the OTM itself, do we have, I mean, such a variation, wherein the OTM itself says that okay, I will establish the membership in the constant amount of the time, but I would only be true say two-third of the time, and one-third of the time I may also be incorrect.
But isn't that the definition of
Yes,
yeah,
so similar, something similar to
yeah.
the randomized complexity classes, uh, but not the complexity class as such, because there we use the normal Turing machine. And here the OTM itself
Huh,
says that, yeah.
yeah, yeah. So what you are saying is that we are giving Oracle access to RP class, and that is what.
My probably I do not understand the difference in between giving the access to the RP complexity class, one thing, or working with a different or a variant of the Oracle Turing machine, and which has got this uncertainty built in. That the Oracle Turing machine, like say in this case, if I ask the Oracle Turing machine that is this Boolean formula satisfiable, so quite possible that the OTM may say no, but then indeed this could be satisfiable. So I'll have to ask OTM probably multiple number of the times, and till I become satisfied. that okay, yes, this OTM is whatever OTM is saying is now I have asked OTM sufficient number of the times
Hmm.
that OTM is saying right.
Hmm.
That sort of.
Hmm. Okay. So, hmm. I think there are models like that, and I think we are what we are. I think this is the same as, I mean, I think both are equivalent. Saying OTM has some kind of a guarantee, some probability associated with it, and it being given access to RP or BPP. And I mean, I'll because I'm not very sure at the moment how that is defined. Oracle access to a class. I'll look into it, and we can discuss this in the next tutorial.
Sure, 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 sure. Yes, yes. Right.
Okay.
Thanks.
And I think just one last question for today would be, this is very similar to what we did just now. So we'll just go through a high level idea for this.
So like in this case, the max click is that does this G have a max click of the size
Hmm.
exactly K?
Hmm.
Yes, so because this click, uh, okay, so yes, so this click is NP complete, and this satisfiability can be reduced into the click problem. Uh, that is how the click
Okay.
problem is NP complete.
Hmm.
So since I'll get the answer of an instance of the satisfiability in the constant amount of the time from the OTM, and an instance of the satisfiability can be rephrased into an instance of the click problem. So indirectly, this is asking like, so whether this, I mean, satisfiability, do we have exact k number of the solutions of the satisfiability, probably something, uh, or do we have yes, I mean, K should come into the picture while establishing that whether this string is a part of the satisfiability or not, and then we can reduce it to the max click to prove this thing.
Yeah, that is, yeah, that is correct. So what the main idea here is, uh, exactly what you asked. So what you said. So I we know that satisfiability reduces to click. So what we will do is, sorry, click reduces to satisfiability. Okay. So what we will do is, we have this graph G, and we want to check whether there's a click of size of maximum size k. So what we'll do is, first we will ask the oracle whether.
Uh, 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 Probably this would be satisfiability will get reduced to click, because then we
Mm,
would like to show that click is at least as hard as the satisfiability problem is. And since
uh,
satisfiability can be complete, so then we used to show that the click is empty complete. Is this not the case here this time
so
in this question?
okay, so what we want is that I want to ask whether there is a click of size k in G. Okay, but I don't have access to click that is given to me. I only have access to sat. So what I'll do is, I'll convert this G instance into a phi instance, and now ask the oracle.
Oh, all right, and yeah, fine. Yeah, I
Yeah.
understood. Fine.
So then the answer to oracle will, yeah, then that will tell us whether, okay, whether G has. Here we will ask OTM, and it tells us whether, okay, does G have a click of size k, or a k click. So if the answer is no, then we are anyway done, then we will reject. If the answer is yes, then it could be that there is an exactly k size click, or there is a greater than k size click. So in this, so this is what we need to differentiate. So all you need to do is, again, now ask whether there is a, yeah. So how do we differentiate between these two cases?
So if G have a K click, if the answer is no, then we simply reject. But if the answer is yes, so and, what's the question that how to show that? I mean, what's the question? I could not
is
understand that.
how to differentiate whether there is a click of size exactly k or greater than k, because we want to say yes only in this case.
So what you can do that we can bring this. So we while converting this instance of the click into satisfiability thing, we would like to have everything in the clausal form. In the CNF kind of a thing, so that if G has a K click, uh, G has a K click would mean that so if since this I mean so how are we reducing the click instance into an instance of the satisfiability, that if a vertex is a part of the click,
Hmm.
so then the variable corresponding to that vertex should be the part of that clause, so that that clause comes out to be true, probably in that way. So if so, basically we would be asking uh, OTM. Oh, I see. If we are not doing it this in the probably the clausal form, I don't know. Because I borrowed this idea from the proof wherein we used to reduce satisfiability into the click to show that click is also NP complete. So there we take the help of the clausal format. But in this case, so does G have a K click? And if I ask this to the OTM, and OTM is meant for the satisfiability only. This is the case.
Okay.
So then,
Okay, so for now let's assume that instead of sat you actually have access to the click. Okay, you are, let's say for now that you are directly using the click oracle. So the first query that we asked was whether there is a click of size k, and if it said no, we are fine. If it says yes, that means there could be a click of size exactly k, or there could be a click of size more than k. Okay, so now can you just ask one query to click again, click oracle.
so does this have a click of the size less than k?
Mm,
I will ask this query. So if it says that it is
but less than k
not
was
less than,
anyway rejected.
oh,
Hmm.
less than k was rejected. Okay. Uh,
So if it has a click of size k plus 1, that will solve our uh, problem, right? Because if it has a click of size k plus 2, it will definitely have a click of size k plus 1. So anything more than k that is there will always say yes for this.
uh,
Because I mean, if it has a click of size k
yes, yes,
plus
yes,
huh,
yes, yes,
huh,
yes. For if it is if for greater than k, if it says yes, and if we have a click of the size k plus two, then certainly we have a click of the size k
k
plus one.
plus 1 exactly. So we will
But but it guarantees for k as well. Then I mean it would be true for k as well.
but we want exactly k, so this will say no if there is only a click of size k and no click of
Yes,
size
yes,
k
yes.
plus. So we will ask oracle for one more query, and if it says no, then we will accept. If it says yes, then we will reject.
Yes, yes.
Okay, so yeah, the details of how we convert this click to sat is, yeah, is similar to what we did, I mean, earlier. So we will not get into the details of that, but we do know that that does exist a polynomial time reduction, so we will rely on that. Okay, so okay, so I think we'll end the session today uh, earlier. So next we will meet on um, Saturday 9 a.m. to 11 a.m. And yeah, I will upload it by tomorrow, the remaining session.
Yes, sure. You take your time for this remaining session because I would be seeing that session on weekend only.
Okay, okay,
Yes,
okay.
and I mean for this session on weekend, which topic shall we cover?
I And I'm not sure, I didn't look into the, and so basically, so whatever is being covered in that week 6, right? uh, NPTEL course week 6
Okay,
lecture, it will be the same.
okay, perfect. Thank you so very much.
Okay,
Thanks.
thank you.
Bye.
Bye.